Hello everyone and welcome back to the Algebra video lecture series. Today we are going to be starting a new chapter and a new topic called radical expressions. Radical expressions are things like square roots, which you might have seen before. So the square root of a positive number a is the number whose square is a. So for example, we're going to be evaluating things like the square root of 16. So when you're evaluating the square root of 16, what you're asking yourself is, what number times itself gives me 16? Well, 4 times itself gives me 16, so the square root of 16 is equal to 4. Another word for the square root symbol is called a radical. And there are actually going to be different types of roots, which is why we kind of all lump them together into this one term called radicals. Now, a radical can also be written as an exponent, and those exponents are going to be fractions. So a radical can be written as a rational exponent. So the square root of x can simply be rewritten as x to the power of 1/2. These are two different methods of writing the exact same thing, so radicals can always be written as exponents. And since radicals can always be written as exponents, they do have a place in order of operations. Because radicals can be rewritten as exponents, radicals are always done at the same time as exponents in order of operations. Now, you might also remember that -4 times -4 is also equal to positive 16 because a negative times a negative is a positive. So yes, -4 squared is also equal to 16. However, we're going to be focusing on what is called the principal square roots in this class. So the positive number whose square is 16 is called the principal square root. So since positive 4 since positive 4 squared is equal to 16, 4 is going to be the principal square root. And unless the problem tells you to do otherwise, you're always going to default to finding the principal square root or the positive square root. We're probably not going to get to this in this class, but just as a disclaimer that when you use square roots to solve quadratics, those are the main exceptions to this. Now, because radicals can be rewritten as exponents, they are done at the exact same time as exponents in order of operations. Also, anything that is underneath a square root can be thought to have parentheses around it. So when you have things that are both inside of a square root and not inside of a square root, the numbers that are written outside of the square roots are technically multiplication. So for negative square root of 16 here, because exponents come before multiplication, we're going to do the square root of 16 first, which is 4. And then that negative that is in the front is just going to stay there, giving you a final answer of -4. Now, another term for the number that is inside the square root is called the radicand. So 16 there is also called the radicand. Now, the square of a whole number is called a perfect square, and you've seen a lot of perfect squares before. Perfect squares happen when you take whole numbers and you square them. So, for example, 2 squared is equal to 4, 3 squared is equal to 9, 4 squared equals 16, and you get the idea. So numbers like 4, 9, 16, etc. are called perfect squares. If you remember your multiplication charts, the numbers along the main diagonal, which were usually highlighted in a different color, the numbers along the main diagonal of the multiplication chart are the perfect squares. So perfect squares happen when you take a whole number and you square it. Now, if you have a perfect square inside of a square root, it comes out to a whole number. We already saw this. The square root of 16 came out to the positive number 4, and it's a whole number, so the square root of 16, because 16 is a perfect square, the square root of 16 came out to a whole number. So what we're going to do is we're going to find each of these. So for the square root of 49, what you are asking yourself is, what number times itself gives me 49? Well, 7 times itself is 49, so the square root of 49 is equal to 7. So then for this next one, for the square root of 81, we are asking ourselves what number times itself gives me 81? Well, 9 times itself is 81, so the square root of 81 is equal to 9. For square root of 144, we're asking ourselves what number times itself gives me 144, which is 12. For the square root of 9, we are asking ourselves what number times itself is 9? Well, 3 times itself is 9, so the square root of 9 is equal to 3. For square root of 4, we are asking ourselves what number times itself is 4, which is 2. And then for this last one, remember, anything that is inside of a square root needs to be done first, and then anything that is not inside of a square root will be done later. So I'm going to focus on doing the square root of 25 first, which is going to be 5. And that negative that was in front will stay there, giving us a final answer of negative 5. Now, not every number inside of a square root is going to be a perfect square. So if the number that is inside of a square root is not a perfect square, you can only approximate it. It is not going to come out to a whole number. So for example, the square root of 2, if you do this on a calculator, you get 1.4142 blah, blah, blah. It's a decimal that never ends, so it never terminates, and it never repeats. This is what is called an irrational number. Irrational numbers are decimals that can never repeat and never terminate. So radicsans that are not perfect squares are irrational numbers. So since they're not whole numbers, you may be able to simplify them. And that is what we're going to focus on for this first section here. Now, before we get into that, we do need to cover a couple of important properties of radicals. This first property is called the product property of radicals. And what it says is that if you have a product inside of a radical, you can break it up into the product of two separate radicals. So the square root of a times b is going to be the square root of a times the square root of b. The next property that we're going to cover is called the quotient property. This property is mainly used when you're taking the square roots of fractions. So if you have a quotient inside of a radical, you can simply take the radical of the top and the radical of the bottom. So the square root of a over b can be simplified as the square root of a divided by the square root of b. So what that means is that you can break up multiplication and division inside of a square root or any other radical. You cannot, under any circumstances, break up addition or subtraction inside of a square root. So do not do this. Do not simply take the square root of a plus b and write it as the square root of a plus the square root of b. Do not do this. You cannot break up addition or subtraction that is inside of a radical. Now, the product property of radicals specifically is at the heart of this process called simplifying square roots, which is what most of your homework is going to be about. So this involves when you have a radicand that is not a perfect square. What you're going to do is you're going to find what is called the largest perfect square factor of the radicand. Perfect squares are numbers like 4, 9, 16, 25, 36, etc. And you're going to find the largest of those perfect squares that goes into your radicand. So some of these are going to be really easy to figure out and other ones are not. So what you can do is take a calculator, which you are allowed to use, take the number inside of your square root and start dividing them by 4, 9, 16, all the perfect squares. If your division comes out to a whole number, that means that number was a factor. If you do not get a whole number and you get a decimal, that number was not a factor. And you're going to keep trying this until you either find the largest perfect square factor or you run out of perfect squares to try. Then, once you have figured out the largest perfect square factor, you're going to write the radicand as a product of that perfect square factor times whatever the calculator gave you as a quotient. Then you're going to use the product property of radicals, and you are going to break it up into the product of separate radicals and finish simplifying. Now, the square root of a perfect square will come out to a whole number. The square root of things such as 2 can't be simplified. So here's how to know when you're done. When the radicand has no more perfect square factors or is a prime number, then the radical is fully simplified. For example, for the square root of 2, 2 is a prime number and 2 is not a perfect square, so square root of 2 would be fully simplified. So would square root of 3. Square root of 3 is a prime number, it cannot be simplified. You're also going to run into this a lot. While 6 is not a prime number, 6 has no perfect square factors because 6 itself is not a perfect square, and its only factors are 2 and 3, which are also not perfect squares. So, since 6 has no perfect square factors, square root of 6 would be fully simplified. Same thing with square root of 10. 10 is not a perfect square, and its only factors, 5 and 2, are also not perfect squares. So, since 10 does not have any perfect square factors, square root of 10 would be fully simplified. So we're going to simplify each of these. So starting with the square root of 32, yes, 4 does go into 32. But there is a larger perfect square that goes into 32. If you do 32 divided by 16 on a calculator, you get 2. So 16 is actually the largest perfect square factor. So I'm going to write 32 as the square root of 16 times 2. Then I'm going to break this up into the product of two separate square roots. So I'll write this as the square root of 16 times the square root of 2. And then I'm going to do all the square roots that I can, and then any square roots that I cannot evaluate and have come out to a whole number, I'm going to leave alone. So the square root of 16 is the whole number 4. The square root of 2 is not a whole number, so we're just going to leave it as the square root of 2. So then 4 square root of 2 is fully simplified, and this is your final answer. I do not want a decimal approximation for these. This is what is called leaving your answer exact. I don't want to know what 4 times the square root of 2 is on a calculator. I don't need to know what decimal that is. You're going to leave it as 4 square root of 2. So then for this next one up here, the square root of 75, we're going to find the largest perfect square factor that goes into 75. So if you do 75 divided by 25 on a calculator, you get 3. So I'm going to rewrite 75 as 25 times 3. So I'm going to break up this product into a product of two separate square roots. So I'm going to break it up as the square root of 25 times the square root of 3. Square root of 25 is the whole number 5. Square root of 3, since 3 is not a perfect square, this is fully simplified, and we're going to leave it as the square root of 3. And since our radicand 3 has no more perfect square factors, we are done, and this is our final answer. So then for the next one, for the square root of 12, we're going to find the only perfect square that goes into 12, which is 4. So 12 is 4 times 3. So then I'm going to break this up into the product of two separate square roots. So I have the square root of 4 times the square root of 3. Square root of 4 is 2. Square root of 3 cannot simplify, so we're going to leave it as the square root of 3. So then for this last one, for 72, yes, 9 does go into 72, but there is a larger perfect square that goes into 72. If you do 72 divided by 36, you get 2. So I'm going to rewrite 72 as 36 times 2. Then I'm going to break this up into the product of two separate square roots. So I'm going to write this as the square root of 36 times the square root of 32. Sorry, times the square root of 2. Square root of 36 is the whole number 6. Square root of 2 cannot be simplified, so we're going to leave it as the square root of 2. So 6 square root of 2 is our final answer. And then we're going to do that for each of these. So for the square root of 360, if you do 360 divided by 36, you get 10. So that means 36 is a perfect square factor. So I'm going to rewrite this as 36 times 10. Then I'm going to break this up into the product of two separate square roots, into the square root of 36 times the square root of 10. Square root of 36 is the whole number 6. Now 10 is not a perfect square, and it does not have any perfect square factors. Its only factors are 5 and 2. So the square root of 10 is actually fully simplified. So 6 square root of 10 is our fully simplified final answer. Now for 3 square root of 90, notice how the 3 is outside of the square root. Remember, square roots are always done before multiplication, and there's technically hidden multiplication right there. So what I'm going to do is I'm going to focus on simplifying the square root first, get that fully simplified, and then once that is finished, then I'm going to take care of this times 3 that is outside of the square root. So for square root of 90, we're going to find the perfect square factor of 90. If you do 90 divided by 9, you get 10. So I'm going to break it up into 9 times 10. Then again, I'm just going to leave this 3 where it was in the front. I'm going to split this up into the product of two separate square roots. Then I'm going to evaluate all the square roots that I can, and any square roots that I cannot evaluate, I'm going to leave alone. So I'm going to leave that 3 alone. Square root of 9 is equal to 3. Square root of 10 cannot be simplified, so we're going to leave it as the square root of 10. Now that the square root is fully simplified, now I'm going to multiply together any numbers that are not inside of a square root. So 3 times 3 gives me 9, square root of 10, and I'm going to leave it like this. So then for the last one, again, if you have no idea what the perfect square factors are, you're going to start by taking 252 and you're going to divide it by a bunch of perfect squares. So if you do 252 divided by 4, you get 63. There's probably a bigger one. If you do 252 divided by 9, you get 28, which is better, but again, you might find a bigger one. The biggest perfect square factor is actually 36. If you do 252 divided by 36 on a calculator, you get 7. So I'm going to rewrite 252 as 36 times 7. Then I'm going to break this up into the product of two separate square roots, so the square root of 36 times the square root of 7. Square root of 36 is 6. Since 7 is a prime number, that square root of 7 cannot simplify, so this is going to be our final answer. Now, negatives outside of square roots are not a big deal because they are considered separate. Negatives inside of a square root are a problem. So for the square root of negative 36, what you would be asking yourself is what number times itself gives me negative 36, which isn't possible. Because if you do negative 6 times negative 6, a negative times a negative is always a positive. So there is no number that times itself will give you negative 36. So you just can't do this. There is no square root of negative 36. So we're going to say that the square root of a negative number is what is called either non-real or undefined. So the square root of a negative number is not a real number. Now, when you have a variable inside of a square root, you do need to pay attention to what the exponent on that variable is, because you might be able to simplify it depending on what the exponent is. So if the power on your variable is exactly equal to 2, as you notice, the square roots of perfect squares come out to whole numbers. And taking the square root of a perfect square will undo each other. So what will happen is if the power on your variable is exactly equal to 2, the power and your radical will cancel each other out, leaving you with just your variable. Now, if the power on your variable is higher than 2, that means it can be simplified. And what you're going to do is you are going to rewrite that variable in terms of as many powers of 2 as possible. You're going to write it in terms of as many squares as possible. So what you will ask yourself is, how many times does 2 go into this power? And how much is left over? Now, if the power on your variable is lower than 2, it cannot be simplified any further. So for example, we're going to take the square root of a to the 6th and we're going to simplify it. This power 6 is obviously higher than 2, which means that we can simplify it. So we're going to rewrite a to the 6th in terms of as many a squareds as we possibly can. So what we'll ask ourselves is, how many times does 2 go into 6? Well, 2 goes into 6 3 times. So I'm going to write this as a squared times itself 3 times. This is basically the reverse of the product property of exponents, because 2 plus 2 plus 2 will give you 6. Then, once you have a product inside of a square root, we're going to write it as the product of 3 separate square roots. So we'll write it as a square root of a squared times another square root of a squared times another square root of a squared. Then, any time that your power is exactly 2, the square and the square root will cancel each other out. So square root and square will cancel each other out, leaving you with a. Then square root and square will cancel each other out, leaving you with another a. Then square root and square will cancel each other out, leaving you with another a. And then a times itself 3 times can be written as a to the 3rd power, and then that is going to be our final answer. So then for the next one, for x to the 7th, the power 7 is higher than 2, so that means this can be simplified. So I'm going to rewrite x to the 7th in terms of as many x squares as I possibly can. So what we're going to ask ourselves is, approximately how many times does 2 go into 7? Well, approximately 3 times with 1 left over. So I'm going to write x to the 7th as x squared times itself 3 times, with an x to the power 1 left over, because 2 plus 2 plus 2 plus 1 is 7. Then I'm going to split this up into the product of 4 separate square roots. So I have the square root of x squared times another square root of x squared times another square root of x squared times the square root of x to the power 1. Anytime your power is exactly equal to 2, the square and the square root will cancel each other out. So this square will cancel out with this square root, leaving you with x. This square will cancel with that square root, leaving you with x. Square and square root cancel each other out, leaving you with x. Now for the square root of x to the power 1, the exponent 1 is smaller than 2. So since the exponent is less than 2, it cannot be simplified, so I'm going to leave it as the square root of x. Then, to finish this up, I'm going to multiply everything that is not in a square root together. So x times itself 3 times can be written as x to the 3rd. And then I have this leftover square root of x. There's hidden multiplication there, remember? And then that is going to be our final answer. So then for b to the power of 15, we're going to do the same thing. 15 is higher than 2, so this can absolutely simplify. So we're going to ask ourselves, about how many times does 2 go into 15? Well, 2 goes into 15 about 7 times with 1 left over. So I'm going to rewrite this as b squared times itself 7 times. with a b to the power 1 left over. Because 2 plus 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 1 gives us 15. Then I'm going to break this up into the product of several separate square roots. So I have the square root of b squared times another square root of b squared times a third square root of b squared, and we're going to have 7 of these. So 4, 5, 6, and 7. I'm out of room. And then we have this extra square root of b to the 1 left over. So then any square roots and squares performed together will cancel each other out, and we're going to have 7 of them. So those cancel out, leaving you with b. Those cancel out, leaving you with another b. Those cancel out, leaving you with another b times another b. And we're going to have 7 of these in the end. Then that square root of b to the power 1, because the exponent is smaller than 2, it cannot be simplified, so I'm going to leave it as the square root of b. Then I'm going to multiply everything that does not have a square root altogether, so b times itself 7 times can be written as b to the 7th, times square root of b is going to be our fully simplified final answer. So let's kind of put it all together for these next two. We're going to simplify any numbers that are inside of the square roots like we normally would by finding perfect square factors. And we're going to simplify any variables that are inside square roots by writing it in terms of as many squares as possible. And remember, there is multiplication here between these two, between the 24 and the x to the 5th. So if you want to, you can split this up mentally into the square root of 24 times the square root of x to the 5th, and then you can simplify one at a time. So for the square root of 24, we're going to find the only perfect square factor that goes into 24, which is 4. So if 24 is going to be 4 times 6. Then for the square root of x to the 5th, since 5 is bigger than 2, it can be simplified. So we're going to rewrite x to the 5th in terms of as many x squareds as we possibly can. So 2 goes into 5 approximately 2 times, with 1 left over. So then I'm going to break this up into a whole bunch of separate square roots. So I'm going to break this up into the square root of 4 times the square root of 6 times the square root of x squared times another square root of x squared times the square root of x to the power 1. Then I'm going to do any square roots that I can, and any square roots that I cannot do, I'm going to leave alone. So the square root of 4 is the whole number 2. Square root of 6 is not a whole number, and 6 does not have any perfect square factors, so I'm going to leave this as the square root of 6. Then for the square root of x squared, square root and square cancel each other out, leaving you with x. Then for square root of x squared, they cancel each other out, leaving you with x. Then for square root of x to the power 1, since that power is lower than 2, it cannot simplify, so I'm going to leave it as the square root of x. So then to finish simplifying this, anything that is not under a square root, I'm going to multiply together. So 2 times x will give us 2x squared. Then I'm going to put anything that is under a square root together. So square root of 6 times square root of x can be written as the square root of 6x. And then this is going to be our fully simplified final answer. So then for this next one, remember in order of operations, exponents or radicals always go before multiplication. So since there's multiplication between that 2x and that radical, the 2x is technically separate and it's going to be done separate. So I'm going to first focus on simplifying the square root first, and then I'm going to take care of that times 2x. So I'm just going to leave the 2x there. And since this is all multiplication underneath this square root, you can break this up into the square root of 18 times the square root of x to the 3rd times the square root of y to the 10th. So again, leave the 2x alone. For the square root of 18, 18 is not a perfect square, but it does have a perfect square factor. 9 goes into 18. So I'm going to rewrite 18 as 9 times 2. Then for the square root of x to the third, since 3 is bigger than 2, this can simplify. So I'm going to rewrite x to the third as x squared times x to the power 1. So then for y to the 10th, 10 is higher than 2, so I'm going to write this in terms of as many y squareds as I possibly can. So 2 goes into 10 5 times, so I'm going to write this as y squared times itself 5 times. Then I'm going to split this up into the multiplication of a whole bunch of separate square roots, so I've got 2x times square root of 9 times the square root of 2 times the square root of x squared times the square root of x to the 1. Then I'm going to have the square root of y squared times itself 5 times. So root y squared. Hopefully I'll have enough room. Barely. Then any square roots that I can do, I'm going to do, and any square roots that I cannot do, I'm going to leave alone. So again, just leave this 2x alone. Square root of 9 is equal to 3. Square root of 2 cannot simplify, so we're going to leave it as the square root of 2. Then square root and square will cancel each other out, leaving you with x. For square root of x to the power 1, since that power is smaller than 2, it cannot simplify, so I'm going to leave it alone. Then, for all of these square roots of y squareds, all of the square roots and the squares will cancel each other out, leaving you with a whole bunch of y. So we'll have y times another y, and there's actually going to be 5 of them. Then, now that the square root is fully simplified, now we get to look at all of this as one giant string of multiplication. So to finish simplifying, we're going to multiply anything that is not in a square root together first. So 2 times 3 will give us 6. X times x will give us x squared. And then y times itself 5 times will give us y to the 5th. Then we're going to take anything that is in a square root and we're going to combine them. So square root of 2 times the square root of x will simplify as the square root of 2x. And then this is now our fully simplified final answer. So we're going to do basically the same thing for this next one. Remember, anything that is not inside of a square root needs to be considered separate. Square roots are always done before multiplication. So I'm just going to leave this 3x alone out front for now. And I'm going to focus on simplifying everything that is in the square root. So I'm going to break this up into the square root of 8 times the square root of x cubed times the square root of y to the 13th. So leaving the 3x alone, I'm going to work on simplifying each square root one at a time. So for the square root of 8, the only perfect square factor that goes into 8 is 4, so I'm going to rewrite 8 as 4 times 2. Then for the square root of x to the third, because 3 is higher than 2, this can simplify. So I'm going to rewrite x to the third as x squared times x to the power 1. Then for y to the 13th, 13 is a lot higher than 2, so this can simplify. 2 goes into 13 about 6 times with 1 left over. So I'm going to have y squared times itself 6 times. With a y to the power 1 left over. Then I'm going to break this up into the products of a lot of different square roots. So I have 3x times the square root of 4 times the square root of 2 times the square root of x squared times the square root of x to the power 1. Then times square root of y squared times another square root of y squared. We're going to have 6 of these, so there's 3, 4, 5, and 6. And then we're going to have a square root of y to the power 1. Any square root that can be evaluated, you're going to evaluate, and any square root that cannot be evaluated, you're going to leave alone. So I'm going to leave the 3x alone. Square root of 4 is 2. Square root of 2 cannot simplify, so we're going to leave it as the square root of 2. Then square root and square cancel each other out, leaving you with x. For square root of x to the power 1, since 1 is lower than 2, this cannot simplify, so we're going to leave it as the square root of x. Then for the square root of y squared, square root and square are going to cancel each other out, leaving you with y. Square root and square cancel each other out, leaving you with another y. And then we have another y. And another one. And we're going to have 6 of them in the end. Then for that last one, for that square root of y to the power 1, because this exponent is smaller than 2, we're going to leave it as the square root of y. Now that the square root has been fully simplified, now we can take a look at everything that's being multiplied, and we're going to multiply anything that is not in a square root together first. So 3 times 2 will give us 6. X times x is x squared. And then y times itself 6 times is y to the 6th. Then we're going to combine all of our square roots together. So square root of 2 times square root of x times square root of y can be combined as the square root of 2xy. And then this is going to be our final answer. So what you can do is there are some instances where if you have addition or subtraction inside of a square root, especially with, quadratics like x squared plus 6x plus 9, if you can write it as some quantity being squared, a square root and a square will always cancel each other out when they are performed together. So for this square root of 25 times x plus 2 squared, this is 25 times square root of x plus 2 squared. So I'm going to split this up into the product of two separate square roots. I'm going to write this as the square root of 25 times the square root of parentheses x plus 2 squared. The parentheses are actually extremely important because the parentheses mean that everything inside the parentheses, the x and the plus 2, are both being squared. So then the square root of 25 is equal to 5. Now because the parentheses are there to keep the x plus 2 together, you're just going to keep them together. And notice how they are being squared. We have a square root and a square being performed together at the same time. When that happens, they're going to cancel each other out, leaving you with what was in parentheses x plus 2. And yes, the parentheses are still there even after the square root and square cancel each other out. So then I'm just going to finish simplifying this by distributing the 5, so that gives us 5x plus 10, and then that is going to be our final answer. Now for x squared plus 6x plus 9, do not write this as the sum of 3 separate square roots. You cannot split up addition inside of a square root, so do not just split this up and add them together. What we can do is we can factor this. So we're looking for two numbers that multiply to 9 and add up to 6, which are x plus 3 and times x plus 3. Anytime that you have anything times itself can be rewritten as an exponent, so x plus 3 times itself can be rewritten as x plus 3 parentheses squared. Then, when you have a square root and a square performed together at the same time, they are going to cancel each other out, leaving you with parentheses x plus 3. So again, if you want to try these on your own, just pause the video and then resume when you're finished. But this next one is going to be very similar. We're going to break up the hidden multiplication that is right there into the multiplication of two separate square roots. So I'm going to break this up into the square root of 16 times the square root of parentheses x plus 5 squared. Then the square root of 16 is 4 times the square root and the square cancel each other out, leaving you with parentheses x plus 5. Then we're going to distribute 4 to finish up, so that will give us 4x plus 20 as our final answer. So then for this last one, because you cannot break up addition or subtraction inside of a square root, for something like x squared plus 10x plus 25, if you're going to simplify this, you need to think factoring. So two numbers that multiply to 25 and add up to 10 are plus 5 and plus 5. Then, since these two factors are exactly the same, I'm going to write that repeated multiplication as an exponent, so I'm going to write that as x plus 5 parentheses squared. Then the square root and the square will cancel each other out, leaving you with parentheses x plus 5 as a final answer. So that is it for simplifying radicals. We are not done with radicals yet. We're going to be doing a lot more operations with radicals in the next sections. We're going to add and subtract them, we're going to multiply and divide them, and then we're going to look at some different types of radicals. So thank you all very much for watching, and I will see you in the next video.